Yes, so we will start with the second example. You can see a molecule I've written here. The complex has been written here. Okay, can you name this particular complex, everyone? Students, can you all name this? COF6 3 minus. This is the second example I'm going to explain based on the VBT concept. And once you understand the way of doing it, the rest of it is similar. Okay, so you listen carefully. One I've already explained. The second one also I'm going to explain to you. Yes, very good. Others also can answer. Yes, good. Very good. It's a negative complex. Okay, so the name of the transition metal should be the Latin name. So the name is hexa 6 fluorine is there, no? So hexa, and the ligand name is florido. So florido, hexa, florido, cobaltate, Latin name. Okay, cobaltate, ending should be with ate. So cobaltate and oxidation state you can calculate. Fluorine is -1. -1 into 6 is -6. Take to the other side, it will become +6. And then here you have -3. Okay, so it will be 3 itself. So 3. And name with the ion because they carry a negative charge. Okay, it's an ionic complex, so we should end the name with ion. So here this is the name. Now I will start with explaining the bonding again. Okay, listen properly. So the first thing always what you have to do is find out in which oxidation state this particular metal is. Okay, so cobalt is a transition metal over here. Cobalt transition metal X, I will take here this as X. Okay, you can do that at the side. So I am taking cobalt oxidation state as X, and then here fluorine oxidation state is -1. Like that we have 6 fluorine. So X into, I can write -6 because 6 fluorine is there and the whole charge on the complex is -3. So X is equal to -3 plus 6. So that is going to be +3. So that means this metal ion is also in the +3 oxidation state like how we had the first one. Okay. So after this, what you are going to do is first you write the element. Okay, you write the oxidation state later. First you write the element and its configuration. So your argon, and then write according to the order. Okay, 3 first and then 4s after that. So 3d, 7, 4s, 2. Okay, again they are in +3 oxidation state, which indicates that this metal ion has lost 3 electrons. Okay, and they are in their ion state. So I can write cobalt 3 plus ion. Okay, be careful when you are writing these charges. So charge indicates that 3 electrons they have lost. So I can write it in this way: argon 3 electron means 2 from the 4s and 1 from the 3d. Okay, so remaining will be 3d6 and 4s will not be left with any electrons. So 4s electrons will become 0. Okay, so cobalt ion CO3 plus, this is the electronic configuration. After this you have to write them in their orbital. Okay, so distribute these electrons in their orbital. So I can write orbital of CO3 plus ion, CO3 plus ion. Okay, so I told you, you don't have to take the inner core electrons because they don't participate. The electrons which will be participating here is the d orbital. Okay, and the s. So I will draw the d orbital. 5 divisions we have. So 1, 2, 3, 4 and then 5. Okay, after that we have 4s. Okay, and then after 4s you will see that there is 4p orbital. Yes, I will continue. So what I was telling you here is, when you write the orbitals, okay, we can see there is 3d orbital and then 4s. After that you will have 4p orbital and then The next orbital which will be available after this, okay, that will be 4d. Okay, so all these will be empty, 4d, and then here you have 4p, and this is 4s. Okay, and the first one which we have is the 3d orbital. Okay, so we will distribute the electrons now. 4s, 4p, and 4d doesn't have any electron. The electrons which are present is only in the 3d. Okay, 6 electrons are there, so I can distribute 6 electron here according to again Hund's rule. So 4 and then 5 and then sixth one. Okay, so here 6 electrons I have put. After this arrangement is over, once you have written the orbitals, I told you these are in the initial stage when the ligand has not approached the metal. You are keeping everything ready. Okay, like I told you, you can imagine when you are hosting some function, when the guests are going to come, you keep everything ready. Okay, so depending on that, the guest will come and occupy. So here we are keeping all these things ready. Now we will be taking the ligands who will be approaching. Okay, then after that you get them. Okay, first you keep all these things ready. So next one is the fluorine ligand. Now what type of ligand is fluorine? Fluorine is a weak field ligand. So what do you think will happen? Will these electrons pair up in the 3d orbital? The electrons will not pair up in the 3d orbital because the ligand which is going to come is a weak field ligand. So these are not going to pair up, and they will not give any of their orbital for occupying by the ligand. Okay, they will not give their any orbitals for the ligands to occupy. Okay, so what the ligand has to do, the ligand has to go for the next orbitals which are available over here. Okay, so here these cobalt is not giving them any electrons because they know that these ligands are weak field ligands. So when weak field ligands are there, electrons will not pair up. Okay, so here I can write down. Okay, I'll write the statements in the presence of weak field ligand like fluorine. Okay, the electrons does not pair up. The electrons does not pair up. Okay, so you can go for the next one. We will go for the next orbital. We will keep this as it is. Okay, so I am going to keep this as it is. So we are going to take the next orbital for them to get hybridized. Okay, so we will go for the next orbital. So I will write down here. These orbitals I will keep as it is. Okay, so you draw them as it is. 2 electrons are present in one orbital. The rest, all the 4 orbitals has one single electrons each. Okay, and then we have here 4s orbitals available. 4s is there, and then 4p we have, and then after that, see here 4s and 4p, if you take the number of orbitals which we will get is only 4. But how many ligands are there? 6 ligands are there, no? You can see there COF6 it is. Okay, so when you have COF6, 6 ligands are going to come. So that means we require 6 orbitals. So this won't be enough. So that is the reason I am writing the next orbital also. Okay, there we didn't write. In the ammonia case, we didn't have to write it because that ammonia ligand, when they came, these orbitals started pairing up. So there was a empty orbital available in the 3d orbital. Okay, 2 empty d orbital we got there. So that was the reason here this much was enough. But now since they are not giving us any place to occupy, so we have to search new place. No, so that is the reason we are taking 4s, 4p, and then we are going for 4d orbital. Okay, how many we require? We require total 6. Okay, so 1 4s I am going to take, 3 4p I am going to take, and 2 d orbitals. So these I am going to take for hybridization. Okay, so these will undergo hybridization. So that means 1 s orbital, sp3, and then 2 d orbital, only so much. Okay, this remaining 3d orbital will not participate because how much is required, only so much we are going to take and then mix them. Okay, so after that what you are going to write here is sp3d2 hybrid orbitals, hybrid orbital of CO3 plus ion. Okay, this is for CO3 plus ion. And then you keep this as it is. This I am going to keep it as it is. Okay, that is 3d orbital. This which we have taken for hybridization, that we will mix together. Okay, so here you can just write sp3d2 hybrid orbital. Okay, so 6 are there, no? So 1, 2, 3, 4, 5, 6 I've taken. So this we have mixed together. How many are there? 6 are there. So it is 6 sp3d2 hybrid orbitals. 6d sp3d2 hybrid orbitals. Okay, so once we have kept these orbitals ready, once the orbitals are hybridized, then you can put the electron inside that orbitals. Okay, so after that, what I'm going to do next is putting the electrons of the ligand in that particular orbital. Okay, so when you are writing the next step, you can directly write the complex. Okay, so I can write down here complex. The complex was CO F6 3 minus, because this complex is an indication saying that now the metal ion has been linked with the ligand. Okay, so that is the reason why we are just writing only so much. So you could mention about these electrons which are not taking part. You write them as it is, don't miss them out. Okay, keep them as it is here, 3d orbital. Now these mixed ones I will write together and I will put the electrons inside those orbital. Okay, so we have like that total 6. I will distribute the electrons. So 2 electrons each of the ligand. Okay, that is fluorine ligand. So you can put them like this. Okay, so these are the 6 electrons, 6 pairs of electrons of the ligand. Okay, so after that you write 6 sp3d2 hybrid orbitals. Hybrid orbitals are occupied by 6 fluoride ligands. Okay, they are occupied by 6 fluoride ligands. That's it. So it's very easy, students, if you understand. So once this is over, then you mention the hybridization, their geometry, their magnetic property and everything. Okay, so hybridization is this sp3d2. So if sp3d2 is a hybridization, whenever you see 6, it has to be octahedral. Okay, if you see 6 ligands are going to come, so there is no confusion. Okay, it has to be octahedral. So here it's an octahedral geometry. So once the geometry is over, then you check out whether they are paramagnetic or diamagnetic in nature. Okay, magnetic property we are checking out. So I told you paramagnetic and diamagnetic, when you are calculating, you have to see the metal orbitals. Okay, whether the metal orbitals are paired or in the metal orbitals the electrons are unpaired. So what do you think will be the magnetic property of this particular complex? Yes, very good. Single, no? They are having unpaired electrons. Yes, they are going to be paramagnetic in nature. Very good. So this has to be paramagnetic in nature. Okay. So here unpaired electrons. So don't see for the ligand, because I told you ligands always will be paired, because they are going to get one pair of electrons. Each ligand gets one pair of electron. So you have to check out for the metal. So here they are paramagnetic in nature. Inner orbital or outer orbital complex? What do you think? They are inner orbital or outer orbital complex? High spin, yeah, high spin and outer orbital. If they are outer orbital, they have to be high spin. Okay, so that you can link together and remember. Yes, so done, only so much. So these are the last things. So I will write it down. Hybridization. So hybridization over here is sp3d2, sp3d2. Then we have geometry. Geometry of this particular complex is octahedral. And after the geometry, we have the magnetic property. I will write here, magnetic property. So checking out the magnetic property, we saw that the metal atoms are having unpaired electron. So it is paramagnetic in nature, paramagnetic. If you want, you can write here, okay? Because metal ion has unpaired electrons. They have unpaired electrons. Okay, so they are paramagnetic in nature. And then the last one is the type of complex. So type of complex, we can see the d orbital comes at the end. If the d orbital comes at the end, then it will be outer orbital complex. Outer orbital complex. Okay. Outer orbital complex are always high spin complex. So you can put a slash and write this also. So if you want, I will explain once again. I'll just brief you through this. See from the beginning with COF6 3 minus. First thing what you have to do when a complex is given to you, find out what is the oxidation state of it. Okay, so you can see the oxidation state I have found out here. Okay, cobalt is X. Fluoride ion, you need to remember fluoride ion oxidation state is -1. Okay, only one ammonia ligand you are having, rest all the ligands are having a -1 charge. Okay, fluorine, chlorine, and then cyanide. Only these three ligands you have for this complex. So you can remember that easily. -1, and only for ammonia it is 0. Okay, so here cobalt is X. 6 fluoride ion is there. So -6 I have written. Whole charge on the complex is -3. So -3. So altogether when you do the calculation, you will get as +3. So metal oxidation state over here is +3. Don't see this charge and write down. Okay, there are so many of them who do this mistake also. They see this charge and they write -3. So then it will be wrong, because the metal is in the +3 oxidation state. +3 means they have lost 3 electrons. Okay, so they have lost 3 electrons. So you have to make the loss of 3 electrons from their elemental state and then write them in their ion form. Okay, so I have removed 3 electrons. After writing the electronic configuration, you will understand. So from the last shell, you have to start removing. So here 2 electrons I am removing from the last shell, and 1 electron I have removed from the 3D shell. So you will get 3D6, 4S, 0. Okay. Then put them into the orbital. So orbital of cobalt 3 plus ion. Okay. So I am writing orbital of CO 3 plus ion. In that, distribute these electrons. 6 electrons are there in the 3D. So I have distributed 6 electrons, you can see here. Okay. Then draw the empty orbitals like that only. 4S is empty orbital. 1 division it has. P has 3 division and D has 5 division. So just draw them like that and keep it like that only. So once you are done with the metal part of it, then you go for the ligand. So you can see here there are 6 fluorine ligand which are going to come, and the fluorine is a weak field ligand. So when the weak field ligand approaches the metal atom, these electrons does not pair up. In the metal, the electrons which are present in the orbitals, they don't pair up. Okay, they will remain as it is because they don't have so much power. Weak field ligand doesn't have so much power to get them together. Okay, so these metal, what they have, like this ligand, what they have to do is they have to go for the next orbital now. If they want to occupy the orbitals in the metal, they have to go for the next one, because here they are not allowing them to come and occupy. Okay, so we are going for the next one here. The next orbitals which are available for us is 4s, 4p and 4d. So since there are 6 fluorine ligands, so we are going to take only so many orbitals. So this 1s, 3p and then 2d orbital will undergo hybridization. Okay, to give you those hybrid orbitals. How many are there? So many you take. Okay, so these will give you hybrid orbitals. So we can write down here sp3d2 hybrid orbitals of CO3 plus ion. okay, which has not involved in hybridization, you write it as it is. Keep them as it is. Don't miss them out. Keep them as it is. And this you mix them together. 6 orbitals are combined together and they are having equivalent energy. So like that we have 6 dsp3d2 hybrid orbitals. So these are mixed up and then electrons will be occupied by the ligands. Okay, so ligand will come and occupy this particular hybrid orbitals. Okay, so you can see 6 sp3d2 hybrid orbitals are occupied by 6 fluoride ligands. Then you write down the details of it. So if the hybridization is sp3d2, I told you 6 are there. 6 means it has to be octahedral. So geometry is octahedral. Then you have to check out the magnetic property. To check the magnetic property, you have to see the metal. Whether in the metal orbitals they have paired electrons or they are having unpaired electrons. So if they are having unpaired electron, then it is paramagnetic. Suppose if you find everything is paired up, then you will write diamagnetic. So here we saw that they are having unpaired electron. So we wrote it as paramagnetic. Okay. Then you have to find out what type of complex it is. Since d orbital is outside at the end, it's an outer orbital complex, also called as high spin complex. Okay, third one, you can write down NiCN4 2 minus. NiCN4 2 minus. The name of this complex is 4 cyanide. You can see here. So it's tetracyanido. Again a negative ion. So you have to write the transition name of it. Transition metal's Latin name you have to write. Transition metal's Latin name over here is nickelate. Okay, so it is nickelate. Oxidation state, cyanide is -1 into 4. Yes, -4 and then here this -4 will go that side. No, so -4 will become +4. +4 minus 2 will be 2. So it is 2. And then you end the name with ion. Very good. Okay, so it is tetracyanidonickelate 2 ion. Okay, now I want you people to try out this complex and tell me what is the hybridization you are getting, the geometry and the magnetic property and the type of complex. So nickel atomic number is 28. Nickel atomic number is 28. Remember that. Before that, we will calculate what is the oxidation state of this nickel over here. Okay. Oxidation state of nickel. Nickel I will take as X. Cyanide is -1 and like that 4 are there. So -4 and whole charge on the complex is 2 minus. So -2 I should write equal to -2. So X is equal to -2 plus 4, that is +2. That means nickel is in the +2 oxidation state. Okay. 28 is the atomic number. So if I have to write the electronic configuration, it is going to be argon. Okay. And then we will have 28. No, so 8 electrons will be present in the d orbital and 2 electrons we will have in the 4s orbital. Okay. +2 oxidation state means they have lost 2 electrons. Okay. So I can write here nickel is in +2 oxidation state. Okay. +2 oxidation state. So +2 means I have to remove 2 electrons from here. So I can write it in this way, argon and then 3d8. 4s will be 0. Okay. The electrons present in the 4s orbital is 0. So you can cross check whether your answers are tallying with whatever I'm doing on the screen. Okay. Now after this, what we have to do, we have to distribute this in the orbitals. Okay. So you can write down below that orbitals of Ni 2 plus ion. Okay. So I will take d orbital here, 3d orbital we are having, 5 divisions, 8 electrons are present. So I will distribute all that 8 electrons. So 1, 2, 3, 4, 5 singly occupied, then 3 more remains. So I need to pair them up. Okay, so I am pairing them up. So you can see 3 pairs are there and 2 electrons are singly occupied. So this is for 3d. Okay, so this is for 3d orbital. After that 3d orbital, the next orbital available here is 4s orbital, which is empty. Okay, so we will write that as it is. And then after 4s, the next orbital which is empty is 4p orbital. That also I will draw and keep it as it is. Okay, we may require, because ligands are going to come to the metal atom to occupy this. Okay, so I have kept it as it is. After that, you have to see what type of ligand is approaching this metal. Now cyanide is a strong field ligand. So if a strong field ligand approaches the metal atom, you know this electrons will start pairing up. Okay. So in the presence of strong field ligand like cyanide, I can write the electrons will pair up. So I want you all to write that whole sentence. Okay. I will avoid writing here. Okay. But you will write everything. In the presence of strong field ligand like cyanide, okay, electrons pair up. So electrons will pair up in this presence. Okay. So pairing up means the last electrons which are there, no, that will come over here. Okay. The electron which is present in the 5th orbital will shift to the d orbital because of the strong field ligand. So then the orbital which I have to draw and write will be like this. I will get 4 pairs. Already 3 pairs were there. 4 pairs we will get. One orbital will be empty. Okay, d orbital will be empty, and then you will have one s orbital, and then you draw the 4p orbital. Okay, so here 3d, this is 3d, and this is 4s, and then 4p. Okay, so you will get it like this. Now after that, how many cyanide ions are there? 4 cyanide ions are there. So in the presence of 4 cyanide ion, we require only 4 d orbitals. Okay, 4 orbitals are required. So I will take this one 3d orbital, one 4s orbital, and this one. Okay, 2p orbital is required. Only so much is required for us. This way. Okay, so I need one d orbital, I need one s orbital, and I require 2 p orbital, because total 4 ligands are there, no? So these will undergo hybridization. So what type of hybridization it will be? It will be dsp2 hybridization. Okay, so here this side you have to write dsp2 hybrid orbitals of nickel ion. So I should write here dsp2 hybrid orbitals of Ni2 plus ion. Okay, then draw this. The one which are not taking part in the bonding, you keep them together. So like that we are having 4, no? So this 4 you keep them together. Okay, these 4 orbitals with paired electrons, I will keep them separately. And this 4 which are involved in the hybridization, we will club them together. Okay, so here these are 4 dsp2 hybrid orbitals where the ligand will come and occupy orbitals. Okay, so here 4 dsp2 hybrid orbitals. In this you will put the ligands. Okay, their electron pairs will be occupied over here. So for that you can directly write the complex part. So I will write the complex, that is nickel Cn4 2 minus. Okay, these you draw as it is, 3d orbitals. Okay, having 4 pairs with them as it is, I've drawn. Then I will come to this orbitals which we have hybridize them. Okay, there the ligands will come and occupy. So I will put the electron pairs of the ligand, 2 pairs each of the ligand. So here you can write a statement for dsp2 hybrid orbitals are occupied by 4 CN ligands. Okay, that is cyanide ligands. Then you write the details of it. That is the hybridization. And then after that you have to tell me what is the geometry of it, magnetic property, and the type of complex. Yes, few of them have already finished. Very good. So it is DsP2 hybridization. Yeah, if it is DsP2, the geometry is square planar, magnetic property is diamagnetic, because you can see nickel electrons are paired, and it's a low spin or inner orbital complex. Very good, correct. Others also have got the answers. Hybridization is DsP2. Geometry is square planar. Then you can write the magnetic property. Magnetic property, when you are checking, I told you, you see the metals d orbital. You can check out here inside inner orbitals. You can see all the electrons are paired. So they are diamagnetic. They are diamagnetic in nature. Diamagnetic, you can write the reason, because the electrons in the metal are paired, because the electrons in the metal paired. Okay, and last is the type of complex. Type of complex, that is d orbital is coming inside, so it is inner orbital complex. Inner orbital complex. And inner orbital complexes are always low spin complex. Now one last is remaining. I will give you that also. You can try out. Okay, nickel Cl4 2 minus. NiCl4 2 minus. Yes, the one who has not finished, you can concentrate over here and check out whether your answers are correct. See, nickel oxidation state, this is X, and then chloride ions are there, so -4, and the whole charge is -2. Okay, so oxidation state will be +2. So nickel is in +2 oxidation state. So remember, it is +2. Before that, you can write the configuration. Nickel is 28, so it is argon 3d8 and then 4s2. Since they are in +2 oxidation state, I can write Ni2 plus, so it will be argon and then 3d8. Okay, because 2 electrons are lost from the last shell. So this will be the electronic configuration. After that, you have to write the orbital. So you will write orbital of Ni2 plus ion. Okay, draw that orbital. So d orbital comes first, and then there are 8 electrons. You can see 1, 2, 3, 4, 5, 6, 7, and then 8. Okay, so that is 3d orbital. Then we have 4s orbital, which is empty, and then you can draw 4p orbital also, which is empty. So 4s and then 4p orbital. These are empty. Okay, then you have to see what type of ligand is going to approach the metal. Cl group is the ligand. Okay, Cl is a weak field ligand. So if weak field ligand comes, you know, electrons will not pair up. Okay, Cl is a weak field ligand. Weak field ligand. So electrons will not pair. Okay, electrons will not pair. So when the electrons are not pairing up in the d orbital, they have to go and search for the next orbital which are available. So the orbitals which are available is these 1 4s orbital and 3 p orbital, because they are total 4 in number, no? So these orbitals will be enough for us. So I will directly write here this one step which I used to write before, that you can skip, okay, even in the exam. So what you can write here is these are undergoing hybridization. So you can write sp3 hybrid orbitals. Hybrid orbitals of Ni2 plus In. Okay, this you keep as it is because they are not taking part. So this you keep as it is. 3 pair electrons you can see, and one electron is unpaired. This we will combine them together and write. Okay, so like that there are total 4. So I can write here 4 sp3 hybrid orbitals. 4 sp3 hybrid orbitals. Okay, and last is writing the complex, that is NiCl4 2 minus. Okay, so these are 3d orbital. We will copy it as it is. Okay, and then here when you are drawing the orbital, inside that you have to put the electrons of the ligand. Okay, so that is 2 pair each. So I am putting the electrons of the ligand here. Okay, then you can write 4 sp3 hybrid orbitals are occupied by 4 Cl ligands. Okay, 4 Cl ligands over. Then you write the hybridization part. Hybridization we can see it is sp3. Okay, so hybridization is sp3. If sp3 is the hybridization, geometry is going to be tetrahedral. Okay, so geometry is tetrahedral. And then you have to check out the magnetic property. You can see there is unpaired electrons which are present in the metal. Okay, inside that you can see 2 unpaired electrons are there. So magnetic property is paramagnetic. Okay, so they are paramagnetic in nature. And the last is the type of complex. Okay, so type of complex, there are no d orbital involved, but you can talk about high spin or low spin. So these are high spin complex. Okay, because there are more number of unpaired electrons, so they are high spin complex. Okay, so that's it. It's very easy. It will get over in 3 steps. See, everything will be over here. And then after that, you are just entering the details. What is the hybridization geometry and the magnetic property and type of complex. Okay, so these 3 steps you have to write correctly. And before that, you can see the oxidation state calculation part. Okay, so that you have to keep in mind with the atomic number. So that's it.